Okay, good morning and welcome, warmly welcome to this year's SCAPE. My name is Mietek Bakowski. I'm a manager of Wide-Bandgap Silicon Power Center, lead organizer of SCAPE. We have been organizing workshops with focus on wide-bandgap applications under different names since 2007. And SCAPE is the shortest one of them. So in 2007, the only application was switch mode power supplies with silicon carbide Schottky diodes. The situation is quite different today. So as we all know, wide-bandgap technology is all about energy efficiency. And that means efficient use of electrical energy. The use of silicon carbide and gallium nitride devices in applications means to 50% savings of electrical energy consumption in many applications. And it has a truly revolutionary effect on energy conversion systems due to the drastically reduced conduction and switching losses. So the introduction of wide-bandgap technology in applications has far-reaching implications for technological and industrial development and for economy. Wide-bandgap technology is not a substitution technology. Simply replacing silicon devices with silicon carbide or gallium nitride devices is not sufficient. Taking full advantage of this technology requires and encourages innovations in low inductive package and converter designs, packaging materials, and passive components. Ensuring a high volume of wide-bandgap devices at competitive prices places new demands on material sourcing, wafer size, manufacturing, and testing and screening methods. These issues will be discussed in the sessions on material development and reliability, and in the presentation by Professor Anand Agarwal, previously R&D manager for SiC power devices at Cree, and senior advisor at the US Department of Energy. In short, the ever-increasing demand for electrical energy creates a market for attractive, energy-efficient power electronic products. And wide-bandgap technology enables the realization of such products. The Wide-Bandgap Power Center was founded in 2011 with the aim of promoting the use of silicon carbide devices in applications and creating a platform for collaboration between the power electronic industry, universities, and research institutes. In the opening presentation, Victor Veliadis, Executive Director and CTO of Power America, an organization sharing the same mission, will talk about their program and achievements. Shinsuke Harada, Director of the Advanced Power Electronics Research Center at AIST in Japan, will share the results achieved there. AIST has been the focus of many long-term government-funded development programs for silicon carbide devices and their applications in Japan since the mid-1990s. Over the past 10-15 years, the wide-bandgap semiconductor industry in China has developed impressively across the entire value chain, from material development to electric vehicles. Lubing Zhao from CASA, China Advanced Semiconductor Industry Innovation Alliance, will give us an overview. Positive news from a European perspective is the recent wave of European initiatives that also target wide-bandgap technologies, such as the efforts of railroad companies under the Shift to Rail program to develop and innovate the rail system in Europe, and the PowerISed program, which aims to develop digitized and intelligent power electronics. The latter is in line with a broader vision of closely integrating efficient power electronics and ICT technologies throughout the entire electrical energy system from generation to consumption, a vision formulated by Professor Ohashi of AIST over 12 years ago. An example of recent European initiative on the electronic packaging industry will be presented by Professor Kouqi Zhang. The last successful wave of interest in silicon carbide has now lasted for 30 years. During this time, almost all the concepts in the books on semiconductor power devices have been demonstrated and tested by R&D teams in United States, Asia, and Europe. Basically, only 2 unipolar switching device concepts have made it to commercialization, and those are MOSFET and JFET. And today we will learn from the major silicon carbide semiconductor manufacturers, Wolfspeed, onsemi, ST, and Coherent, about the status of silicon carbide MOSFETs. Gallium nitride is developing at a speed that surprises many, considering that the devices were to begin with normally on, limited in voltage and power density, and based on material with dislocation densities orders of magnitude larger than those in silicon carbide. Today, we have commercially available 650-volt E-mode GaN devices that enable the realization of 3-level converters for the automotive industry. And 1200-volt devices are just around the corner, as we will hear more about from some of the leading GaN device manufacturers, SCAPEAW and InnoScience. Both are here today. Qualification work on wide-bandgap devices is still ongoing in the international community, and automotive applications are particularly demanding concerning reliability. Tomorrow's application sessions are rich with examples from the automotive applications, also including a new area of aeronautics. The application session also includes a presentation on silicon power devices with seemingly provocative title, "The new silicon-based power devices will compete with silicon carbide and GaN devices." This refutes the popular marketing slogan we've heard through many years that silicon carbide takes it all or gallium nitride takes it all, and is a positive reminder that we must learn to live with different materials and different technologies depending on the application. Tomorrow, Elena Barbarini from Yole Group will present a technology and market overview and moderate a panel discussion on power module technologies and design and future packaging trends. Panelists represent power module developers, manufacturers, and users. And this year we have a strong team of panelists from leading players in the field, so please do not miss it. The final session of SCAPE this year will focus on power module packaging, showcasing the development of traditional SiC technology for rail transportation, as well as new embedded power module technologies and GaN power modules for automotive and industrial applications. And already today we can enjoy presentations on power module design and lifetime prediction in the modeling and design session. I hope that this year's event will be a rewarding experience for all of us. Thank you very much. Invite Victor Veliadis to stage. All the speakers should stand here, our team says. We are recording the session, but please, the same policy as every year. We are not distributing any, we distribute material only to attendees of the conference, and we don't distribute anything before you give your acceptance, which means you can delete slides, you can delete the whole presentation. So please do not record or take pictures, anything is not necessary. We will also distribute PDFs with slides. Thank you.
Good morning. It's a pleasure to be here in front of you, and I appreciate meeting. Thank you for inviting me. It's my third time coming to this conference. I'm very excited to share some of the work that we've done at Power America. So my first slide, you've all seen this, this graph here. As Mitek pointed out, there was this big effort between silicon carbide and GaN and silicon, and silicon carbide was going to do it all, then GaN was going to do it all. And in the end, it's really the market that decides what device to be used. And the device to be used has to do with a specific application. We have to look at the voltage requirement, the power density, the current requirements, the efficiency, the type of temperature we need to operate at, and of course the cost to make our decision. And I put a very rough graph together to show this. Silicon, of course, is extremely competitive from 15 to the 600 volt level. Gallium nitride, was mentioned by Mitek, Very competitive from 100 volts up to 900 volts, which is commercial available. And a lot of work is being done to get to the lateral GaN 1200 volt level because of the 800 volt battery electric vehicle applications. And of course, you have silicon carbide. It started at 1200 volts, which is sufficiently distance from that 600 volt where silicon is very competitive. Then you went to 1700, 1.7 kV, 3.3, 6.5, 10 kV. And of course, with the electric vehicle coming, being the economies of scale, the large application, everybody has focused now from 600 to 1200 volts. And unfortunately, the work at the very high voltage that will go towards grid, another high power application, has really fallen behind. So if we were to make a comparison between the different areas of competitive advantages, silicon, of course, we all know it's very reliable, it's rugged, it's cheap, and it's capable of high currents. And very, very importantly, there's device and circuit design legacy, meaning people know how to basically put circuits together with silicon. And as Mitek mentioned, it's not as simple as taking a silicon device out and putting a silicon carbide or GaN device in its place, okay? There has to be knowledge and understanding to take silicon carbide and GaN to their full potential. Silicon carbide, as you can see from the graph, it's very efficient. It can go up to high frequencies, high power, and then GaN can even go into higher frequency as well at decent cost. So again, the application specifics will dictate the type of device to be used. Now, going back in time, what is it that basically spurred this massive growth in silicon carbide technology in the United States? And of course, it was the military applications. I was working on hybrid electric Humvees, hybrid tanks, back in the early 2000s for the United States Army. Doing solid state power helps deploy teams in, in forward locations, makes it very easy. Pulsed power is a huge application. There's electromagnetic railguns, so directed energy weapons. And this is a technology that I was working on, which is basically an electromagnetic shield. It's a way to protect, Army vehicles from projectiles coming their way using high electromagnetic fields, 10 kV type of, MOSFETs and devices. We're fabricating those in the early 2000s, right? And you would expect by 2024 they would be commercially available, and they would have been if it weren't for the electric vehicles kind of jumping in and kind of grabbing the market and focusing the work on the lower voltages. And of course, electric warships and the electromagnetic aircraft launch system, those are all available. And, these applications, of course, are not unique to the United States. I've seen presentations from other countries, China included, and they're also working on electromagnetic catapults for aircraft carriers and other applications. So from the commercial sector, you're familiar with the applications, automotive, consumer electronics, really big, power conditioning in data centers. Electric motor drives is a big one, and then with the higher voltages, the grid infrastructure is a big application. And with any new technology, to become competitive in terms of price, you need to have a killer application, right? Which is going to lead to high volume, take it to economies of scale, and reduce the cost. And of course, we all know that for silicon carbide, this application is the electric vehicles. And the goal is to get to economies of scale. It's really when you get to economies of scale that prices drop and you're cost competitive. So some of the barriers, the remaining barriers, kind of the bigger barriers to mass commercialization are, of course, the high device costs. We all know that silicon carbide as well as GaN are more expensive than silicon, so that's a barrier. Another aspect is defects, right? Mitek mentioned that defects, orders of magnitude, higher in GaN than in silicon carbide. Silicon carbide has defects as well, and that compromises the area, the size of the area that you can make in silicon carbide as well as GaN. The other one is reliability and ruggedness, okay? Everybody today knows that silicon carbide devices are basically can perform at a higher level than silicon. There's no doubt about that. The question that they have is, are they reliable? Number one, right? Will they do the 20 years or 25 years of, of life of the system? And very importantly, are they rugged enough? if something goes wrong, how well will those devices hold out? That's a big question when it comes to the decision of utilizing these devices. And of course, there's the need for workforce training. This area, silicon carbide, GaN, wide-bandgap, has grown massively, and the workforce has not kept up with that pace. So certainly for the United States that I can speak about, there's not enough people, and the same people are changing jobs between the companies, but that's not the way to move forward. So a lot of what needs to be done is train the workforce, bring in people that will use, that understand silicon carbide and GaN technologies. And it's not as simple, we need to do this not simply for economic reasons, right? If we're to meet the emission goals of 2050, if we're to basically clean our planet and pass on a cleaner planet to the next generation, it cannot be done without silicon carbide and GaN, right? They're in every power application. They bring a lot of efficiency, so they're crucial to that equation. So to introduce Power America, these are some of the problems we're solving. We have 90 members. They come from academic institutions. We have a number of universities that we work with. There's a number of companies that do materials, equipment, fab, modules, and there's a number of companies that do wide-bandgap systems. So basically, they insert silicon carbide and GaN into their systems. So what we do, we support wide-bandgap technology across the supply chain, from basically the materials to design, to the equipment in the fab, to the fabrication, the modules, and the applications. And as I mentioned before, wide-bandgap technology is a critical enabler in the electrification of everything, right? That brings efficiency, and it's crucial to decarbonizing and bringing energy sustainability. So with that in mind, the United States back in 2015, under the Obama administration, started the Power America program. It was a $70 million investment from the Department of Energy that was supplemented by another $80 million in cost share. So it was an over $150 million effort. And what we did is we addressed all aspects of the wide-bandgap supply chain, and specifically we worked on chip design, fabrication, setting up fabs, doing the high voltage, high frequency testing, building the modules that allow silicon carbide and GaN to work to its full potential, proving out the reliability, very crucial for customers to adopt silicon carbide. We looked at the ruggedness, and then we did a lot of demonstrations in major applications. And the idea was that you cost share the demo, and the upper management of the company sees the results, understands the competitive advantages that silicon carbide and GaN bring, and then continue the work with their own money. So then you have a taxpayer investment that basically is taken over and grown by the industry. And that has been a very successful model. The early days were the Department of Defense funding these technologies and doing the feasibility studies, showing that it's feasible and there's a way forward. In 2004, 2005, making 10 kV devices, I was using 3-inch wafers from Cree, and those cost $25,000 per wafer, okay? That's a massive amount of money that even the military cannot afford to be paying. So the whole idea is to show feasibility of these technologies and bring them to the point where the commercial sector picks up, brings the volume, reduces the prices, and now the devices are affordable for everybody. So in the end, we completed over 200 projects in all areas of wide-bandgap. And there were many excellent results that moved the sector forward, but I want to point out the silicon carbide fab infrastructure that we build in the United States. And we all know that with the geopolitics today, every country, every region of the world is trying to become self-sufficient in chip fabrication. So in the case of silicon carbide, we fabricated chips in the United States. We led that effort, and we had companies from around the world come to the United States to fabricate, right? So typically what's been happening over the past few decades, there will be major taxpayer-funded work in the United States. Chips will be fabricated, innovations will be made, feasibility will be shown, and that's where things would end. And all the economic prosperity that the US taxpayer funded would take place elsewhere around the world. So this is kind of the exception where the taxpayer put money to develop silicon carbide, and it actually led to high volume manufacturing in the United States itself. So looking at the infrastructure of silicon, you have the IDMs, then you got the foundries. There's fabless companies that go to the foundries to fabricate, and small design houses that basically develop intellectual property that they basically license. And in the case of silicon carbide, we have major companies in the United States fabricating silicon carbide chips. Of course, the silicon carbide fab has particulars. One of them is the fact that you have to have a good supply of quality wafers. And you see this massive vertical integration that's happening in the silicon carbide world, primarily because everybody wants to have the substrate, right? Which is crucial, and it's a big profit margin that you need to pay elsewhere if you don't have it on your own. And of course, the important thing is that silicon carbide does not only compete on the design like silicon, but it also competes on the processing. Every company out there has IP in processing, and they do a lot of the processes differently. And that you can always confirm by looking at the failure mechanisms from devices of different companies. You can see that a lot of them differ because of the different ways that they're making silicon carbide. So with respect to the foundry model, we created XFAB, cost shared. It was a big effort. And the silicon carbide foundry is very particular because you have this process IP. So think about that. You have 50 companies going to a fab, and each company has 5 processes, let's say, of its own. Then you got to support 250 processes in a fab, which basically is not feasible. So we worked with XFAB. I funded and worked with them to do process blocks to cover the majority of the processes and kind of minimize the big number of customer-specific processes that basically would be hard to support altogether. With respect to fabless companies, quite a few of them. Microchip is a company that started out at XFAB, realized the benefit of having silicon carbide, and then turned one of its silicon fabs into doing silicon carbide as well. But all these companies that you see here in the United States ended up going to XFAB under normal circumstances that would, of course, have gone overseas. And finally, there's design houses. And if I can get this to move forward. Okay. If you can advance the slide from your end. Yeah. So that's just basically some universities. Sonrisa is a Purdue professor. And this university basically developed IP that larger companies licensed to get a jump start and be able to compete with people like Wolfspeed and everybody else who's been doing silicon carbide for more than 20 years. So this has been a very successful effort. And of course, you've got these massive companies from overseas, Infineon, ST, and Rome. So it's a very healthy silicon carbide competitive world. Okay, so the first phase of the program ended. We got a renewal from the Department of Energy. It's a $64 million renewal. I'm working out the details as to what we're going to be doing next. But roughly speaking, we're going to run over 60 projects in all areas of the wide-bandgap supply chain. And the objective, of course, is to, in particular with respect to silicon carbide, is to work from the materials, the fab equipment, the chip design, all the way out to demonstrating the competitiveness in applications. So I'm very excited that I'll get an opportunity to do one more run in silicon carbide and GaN. All right, so some of the items that I mentioned, one of them was the high cost of silicon carbide devices. And you can see here that the devices in silicon carbide are obviously more expensive than those of silicon. And roughly speaking, at the lower current levels, lower power, they're 3 times more expensive. Then as you increase the power, they go up in cost. And that's because of the defects, right? The larger you make a device, the more probable it is that you will incorporate a defect, and that will reduce your yields. The cost will go up. So there's kind of a sweet spot as far as the area of the device is concerned. And once you exceed that, you pay more, right? And a big portion of the cost, and I'm sure you all will talk about that, comes from the wafer itself. The wafer itself is anywhere between 40 to 60% of the overall cost, right? And just to give you an idea, this is devices that I was building in the early 2000s, 1.2 10 to the minus 3, very small device, right? You can see there's 10,000, more than 10,000 of those devices on the wafer. And this is the wafer map, the testing. Everything that you see in red is a good device. And for those small devices, I was getting a yield of over 90%, which was really good. And there were, this type of device went into a military aircraft radar system. But when I tried to make larger devices, I wanted the device to be that whole square as far as area is concerned. And I was only able to find 5 squares there that didn't contain a failed device. So when I made the larger area devices, where I had to have every square without a defect, right? My yield went all of a sudden from 92% to 4%, okay? So it's a very steep road getting to high yields and making large devices. Obviously, I wrote a paper about that. I conveniently omitted the yield aspect, but pointed out the benefits in the large area. Okay, so why do we need large devices? Here is a 3-phase inverter back from 2005. And you can see that to get 0.13 centimeters of active area, I needed 216 wire bonds. And a device would fail. I had to look under the microscope to find the burned area. As soon as I increased the size, as you can see here, then instead of needing 216 wires, I only need 9 wire bonds to get more area connected, and then build a half-bridge inverter. So basically, large area silicon carbide devices, wide-bandgap devices are absolutely needed in order to get to the power systems, right? Because paralleling a number of devices is very, very problematic. So large area, big devices, those help compete with silicon. Another issue is, of course, the module is specific to silicon carbide as well as GaN, high voltage, high frequency. And you can see that silicon has very good module solutions at lower cost. That's another cost element for silicon carbide. And the specifics of the module, some specifics are shown here. The most important thing is you got to reduce the inductance, the parasitic inductance to manage the high DIDT. And these long wire bonds, they will not work for silicon carbide. So there's a lot of technology in the module itself. So the bottom line is, if you look at the cost now, okay, the device is very, very expensive, 3 to 5 times more. Well, how is this technology going to be competitive, right? I mean, it's an issue. But you can see here, this is from Infineon. You can see in this cost here, this is the overall cost of the silicon system. This is the overall cost of the silicon carbide system for a PV inverter. And you pay 3 times more for the semiconductor in silicon carbide, but you end up with a system that's cheaper. And the question is, it could be counterintuitive, right? How is it that I pay so much more for the device, but then I end up with a cheaper inverter? And, the solution is rather simple. You go to high frequency, you reduce the size of the passive components, so your overall bill of materials becomes cheaper. So the bottom line is for commercialization, you need to get to price parity, right? You need to be comparable to the cost of silicon, and that can be achieved at the system level because of the reduced weight and volume of the magnetics and the simplified thermal management. And always keep in mind that the cost savings at the system level must outweigh the higher cost of manufacturing the device itself. That is the recipe for successful large volume adoption. And of course, you get lower system losses throughout the life of the system, and that is of course good for the environment. Okay, so last 2 problems. Everybody knows the interface between the oxide and the silicon carbide is one that has a lot of traps that reduces the mobility, right, which is a big part of the channel resistance. That's number 1. And second, it leads to threshold voltage instability, which is a reliability concern. So there's a lot of work going in that area. Another big item with silicon carbide are basal plane dislocations, right, which under electron hole recombination will lead to stacking fold expansion. And you can see here, this is back from 2010 or so, 100 micron device. And as soon as you turn the gate to drain diode on, in the presence of BPDs, you have this drop, and the device is, it's a catastrophic type of defects, right? The performance degrades drastically And I had shown in those days that by annealing this transistor at 350 degrees, you're able to take it back to its original state. So the BPDs find the energy to expand into stacking faults, and then the stacking faults under anneal shrink back to their original state. But anyway, stacking faults is one of the issues when it comes, BPDs and the stacking faults are an issue when it comes to high voltage devices. So that's something to keep in mind. And the last thing is we need a workforce that's trained. So the Power America program spent a lot of effort and money in training students. We trained 430 full-time students that went to industry, went to university, propagated silicon carbide, and we had over 7,000 participants in events. So with that, I hope I gave you an overview of the work that we've done in the past and some of the issues with silicon carbide, and I'm grateful for your attention. Thank you.
Thank you very much, Victor. I suggest, because we have very packed program, and Victor is here all the day, so please grab him during the breaks and ask questions. Talk to him directly rather than we will be running with microphone and allowing two questions or so now. Or if it's accepted, then let's go on.
Thank you.
Yeah. Right. Shinsuke-san, Shinsuke Harada, to give his presentation from AIST. It's on the activities and progress at AIST Japan.
I'm Shinsuke Harada. I'm a Vice Director of ADPAC, our research center. First, I briefly introduce my institute. AIST is a national institute under the administration of METI. METI is the Ministry of Economy, Trade and Industry. And AIST's mission is not pure research, but solving social problems and strengthening the industrial competitiveness. And AIST have 12 based in Japan and 7 domains. And our research center, Advanced Power Electronics Research Center, belongs to main bases of SCAPE and also belong to the energy and environment domains. And our mission is development of power electronics technology based on the wide-bandgap semiconductor material for innovation of energy saving. And based on this mission, we are conducting the consistent and comprehensive R&D for power electronics innovation. This means our R&D target covered from bulk growth to the wafer processing, epitaxial growth, and device process, and package, and module, and inverter system. So we think such a vertical integration for R&D is especially necessary for the new technology development for the new materials. And we have also launched the Open Innovation Collaboration Consortium. It's named TPEC. To accelerate the social implementation of the new technologies. In this TPEC, our AIST is as a core institute and providing the research seed and the main facility and equipment, and also accepting the company researchers. And on the other hand, a company is giving their fund and manpower, materials, and facilities, and bring back the new achievement for the new businesses. And also many universities are joining this project. Advantage of TPEC is by sharing the resource and the accumulated technologies, the company can reduce their R&D cost and risk, and also reduce the multiple investment. This is membership at present. 38 companies and 15 university and 5 national institute joining this TPEC. But unfortunately, all members are Japanese institute or companies because our mission is to support the Japanese industry. Next, I will show you the strategy for the gallium nitride and silicon carbide device development. First, I'll show you the market forecast for silicon carbide and gallium nitride power devices. These are the report by the YOR. Maybe you have already seen. You can see that both silicon carbide and gallium nitride are expected to grow with a high annual rate from 2021 to 2027. So if you see only this figure, you feel the bright future of this material. However, if the market share is compared with silicon, market share is only 30% for silicon carbide and 4.4% for gallium nitride. So, although wide-bandgap device market expected to grow at high rate, we should recognize they are far behind the silicon market. Especially, we think the Japanese company situation is more serious. 1.2 to 3 kilovolt class device have succeeded in commercialization, but in the business phase, a Japanese device company falls behind the company in the EU and the USA. Oh, sorry. This is mainly due to the small scale of investment and fund. Okay. So we should, from a standpoint of R&D, we should accelerate the research for the device chip cost reduction. This is the first priority of the research for the silicon carbide. And also, new device such as high voltage device is necessary to open the new market. This is a second priority for the silicon carbide. And regarding the chip cost reduction device, for example, silicon carbide MOSFET, the cost is compared with silicon ISBT at 1200 volt class. Cost is about roughly 3 times. And the largest component is wafer, and then yield loss, and process, and epitaxy. So to reduce the chip cost, at least 8-inch wafer is necessary, and also more productive process and defect reduction in the epitaxy layer necessary. And reduction on resistance has also important because chip size can be reduced by the low on resistance. And especially superjunction and MOS channel mobility improvement has much important. By this effort, cost should be reduced at least the same level of the silicon ISBT in near futures. And also, for further reduction of chip cost, next generation technology is required. About the SJ technology, we have realized some good results. Low on resistance has been realized in 1.2 to 6.5 kilovolt classes. You can see the red plot in these figures had already exceeded the unipolar limit of the silicon carbide. So we think the superjunction is a big advantage for silicon carbide over the other wide-bandgap materials because other material is difficult to control the p-type doping concentration. Superjunction has some other superior properties. One is the small QRR of body diode. You can see the reverse recovery is much smaller than that of silicon superjunction. This is mainly due to the small lifetime due to the high doping concentration and implanted damage for the SJ process. And the second superior property is a temperature dependence on resistances. This is the example for the 3.3 kV class device. At room temperature, on resistance of full SJ device is about 3.3 million square centimeter. This is extremely low. And with increasing temperature up to the 175 degrees C, on resistance is still low with 6.5 million centimeter. This is the 80% reduction from the non-SJ device of the conventional MOSFET. So this is a big advantage. So we think the superjunction MOSFET will be commercialized in near future. And also, a next generation device will be based on the superjunction, we think. On the other hand, here we talk about strategy for gallium nitride. Recently, impact ionization was experimentally evaluated gallium nitride, and it has been clarified that theoretical limit is almost same as that of silicon carbide. However, a roadmap of power device is still based on the generation change by the material change, like from silicon to silicon carbide to gallium nitride. However, we think the future roadmap should be the breaking the limit of a single material by material composite. For example, silicon carbide has low channel mobility, but have a good quality and reliable breakdown. Also, superjunction has been realized. On the other hand, gallium nitride has an unstable breakdown and immature wafer quality, but channel mobility is extremely high due to the HEMT. And also, recently, most interface quality is improved. So we think that by combining the strong point, extremely superior property will be realized based on this concept. One example of this concept is hybrid HEMT, which we recently proposed. Conventional GaN HEMT has no avalanche capability due to no PN junction. So we think to expand the gallium nitride application to such as motor drive, avalanche capability with a non-destructive breakdown will be necessary. So proposed a GaN SiC hybrid HEMT composed of the gallium nitride HEMT with the SiCPEAW diode, which is monolithically integrated in the SiC epitaxial layers. And we have actually demonstrated the non-destructive breakdown by the avalanche breakdown. Also, we expect the vertical hybrid devices. On resistance of the SiC MOSFET is dominated by the channel resistance. So reduction on resistance is focused on to reduce this channel resistance by employing the trench gates. As a result, a present R&D level trench gate MOSFET is not dominated by the channel resistance. And more recently, super junction has been realized, and as a result, channel resistance again become dominant again. So we expect gallium nitride channel with high channel mobility combined with the silicon carbide superjunction will be the next generation technology, next technologies. Okay, from here I will show you some example of a new market explorer for silicon carbide. First one is SiC monolithic power IC. This is for the high performance operation of silicon carbide, vertical power MOSFET. In case of the conventional gate driver has a distance from power MOSFET. This generates parasitic inductance, result in the limitation of switching speed. So gate driver should be placed as close as possible to the power MOSFET. However, a silicon-based gate driver cannot be placed close to the silicon carbide power MOSFET owing to the heat generation. On the other hand, in case of the monolithic power IC, a gate driver is formed with the silicon carbide and integrated monolithically with power MOSFET. So these two configuration is ultimately close. So high-speed switching speed is possible, and also a smaller size and higher reliability is expected. This is cross-section with the monolithic power IC. CMOS, you can see CMOS is integrated with the vertical power MOSFET. And also you can see the top view of micrograph of the power IC. This is power IC with extremely high switching speed and small lightweight and high reliability will have much impact on this application, such as cosmic device and flying car, and also industrial macinities. And the second example is pulse power by high voltage devices. High voltage and fast switching accelerates the electron, and also discharge and generates high density of plasma. By utilizing this phenomena, we test some applications. First, we fabricate discrete type 13 kilovolt SiC MOSFET and SVD and test the effect on some application. First one is pulse power supply for electron gun, and it is used for the synchrotron radiation facilities. And also pulse power supply is replaced the cyatron switches. And also some other interesting application exist. One is plant growth promoting. Mushroom farmer has experience to grow, that mushroom has grown faster when they have lightning. So pulse power supplied mushroom grow faster than usual. And also water treatment by the plasma is a popular treatment. And also we are developing the ultra high voltage IGBT for next generation intelligent power network. This IGBT can reduce the number of steps of the MMC and can eliminate the transformer, we expect. And also system size is reduced and cost is also reduced. For example, 22 kilovolt SiC IGBT can reduce the number of cells to at least 20%, and the number of parts to the 30% as compared with the conventional 3.3 kilovolt devices. Okay, finally, to conclude my talk, in this talk, I have shown the strategy for silicon carbide device development and device chip cost reduction by new technology and new market explorer by new devices were important. And also we showed the GaN device strategy and reliability issue can be solved by material composites with silicon carbide. And regarding the new market explorer, we have 3 examples. First one is power IC and high voltage MOSFET and ultra high voltage IGBT. Thank you very much for your kind attention.
Thank you, Shinsuke-san. Maybe we do the same as with the first speaker. We are 5 minutes behind, but we just shortened the coffee break from 20 minutes to 15 minutes. Maybe it's enough sacrifice. Not more than that. Okay. So please discuss during the break. We'll ask Lubing Zhao from CASA. Overview of Chinese wide-bandgap industry. Thank you.
Thanks, Mitek. It's my pleasure to attending this meeting first time. And on behalf of CASA, I will share with the development standards and opportunity of wide-bandgap semiconductors industry in China. Okay, my report will have 3 parts. The first part is the demand and the trends in China. Now, wide-bandgap semiconductors are changing the industry ecology, and it's not longer a play. In China, maybe you will heard as known as the third generation semiconductors. In fact, we call the first, second, the third generation semiconductors according to the function of the materials. The first generation semiconductor is maybe the silicon. It's the foundation for the IC industry. And the second is for such as the gallium oxide and the indium phosphide. It's for the information industry. For our lines and this meeting, we focus on the wide-bandgap semiconductors. In China, also call it the third generation semiconductor. Yes, it's mainly for gallium nitride, silicon carbide, also the gallium oxide, diamond. Yes, it's supporting the sustainable development of green, low carbon, and intelligent society. The wide-bandgap semiconductor is the key technology to support smart, green, and sustainable development from the upstream, midstream, and the downstream. China has the world's largest market for the largest, most complex and fastest growing energy internet, particularly for the ultra-high voltage network. And also the hybrid rail transport, and the last growing and the largest new energy vehicle market. Also for the communication market and the solid-state lighting and the commercial industry. Now China has a huge and urgent market needs. In China, the national strategy for the carbon peak and the carbon neutrality strategy, we will have a new power system with new energy as the main body, especially to promote the transitional power grids to semiconductor power grids. And such as the silicon carbide will realize the power electronic device and promote the reliability and the controllability of the energy in connection network. Also, the largest new energy vehicle market and the base station for the 5th generation. Here is the market and application for the technology development. In last year, the production and the sales of new energy vehicles in China reached more than 9 million, and with a year-on-year increase of more than 30% and a market share of 31%. Now there is a large PV installed capacity was ended, year-on-year increase of 148%, and the newly added installed capacity of the new energy storage is about 22.6 million kilowatts, an increase of over 260% compared to the end of 2022. Also, the total number of 5th generation base stations in China reached 3.377 million, and an increase of 1 million compared to 2022. The next part is share the current situation of China's industrial. The industrial in China, I think, entered a rapid development period. First, the technology has gradually matured, and the application field expansion from the commercial to the electric vehicle and the new energy connect. And the industrial technology continues to improve, and the product sales continue to grow. Some enterprises realize the profit. Now here's the China industrial scale in 2023. The total output value of silicon carbide and gallium nitride power electronics in China reached 36.48 billion yuan. For the RF electronics is maybe 7 billion, and the LED optoelectronics, mainly for solid lighting, is 657 billion yuan. Now for the power electronics, in China, silicon carbide mass production is accelerating, and enterprises are actively laying out a trench MOSFET. For the industry, mainly now is the player, but some enterprise are R&D for the trench MOSFET. In China, 6-inch substrate and epitaxy for silicon carbide have achieved mass production. And some manufacturers have basically completed the same delivery of 8-inch silicon carbide substrates. And maybe expanded mass production is about 2025. SBD for the silicon carbide has been widely applied. Silicon carbide for the MOSFETs are being introduced in PV and energy store in China. The electric vehicle drive system will be introduced in small batches in this year, and it is expected to be applied in the next year. Further, we think the two main factors for the silicon carbide in China for the mass production or mass use, maybe the cost, reduce the cost and improving device quality. With the materials of large size, such as 8-inch, and low defense and high yield, cheap miniaturization and new series, new designs, and new technology will for the future. Now, gallium nitride, we think, moving towards broader application areas, from the consumer to industrial and automotive applications, from the voltage to 100 or 600 to higher the voltage. Now, the top Chinese enterprises entered the international supply chain and the global top suppliers list, such as the silicon carbide substrate with advanced market share of 17 and 15 for two Chinese companies, Tianke Heda and Tianyue, respectively. And the both company is entered the infilling supply chain system now. And for the gallium nitride power electronics, already achieving large-scale application in China, gradually increasing market share. But mainly is import now. The Chinese company will increase the share for their market. And for the power electronics market, last year reached 15.32 billion yuan, a year-on-year increase of 45%. And the silicon carbide and the gallium nitride power electronics market experienced a significant increase in scale. In this, the application, the new energy vehicle are the main market driving force, accounting for over 30% of the market, followed by consumer electronics, PFC application, and so on. The new energy vehicles are the largest application field of power electronics in China. Last year, silicon carbide and the gallium nitride device module for new energy vehicle was maybe 10 billion yuan, according to the 70 of the overall market share. It's expected that this market will reach 34 billion yuan by 2027. More than 1 million new energy vehicles in China have used silicon carbide power devices in 2023, mainly from ST, infilling, both Wolfspeed and ROM. Not very little market share for the domestic company, mainly from these 5 companies. Next, the consumer power supplies and the PFC accounting for 11% and 5.8%. Now, it has agreed that Chinese car companies deeply engage with semiconductors, maybe 3 more. First is self-developed by car companies, such as for BYD. It make from the substrate, epitaxy, device, and module, and the system all chain is it have the production, the capability for the silicon carbide. And the second more is establishing a joint venture or joint research and the development with the semiconductor companies, such as maybe is the Guangqi, okay, here's the English name, and Xiaoli, Dongfeng, maybe the Chinese car companies. And the third is strategic investment in power semiconductors, such as Huawei and Xiaopeng. There will be give the funds to the startup and some chain industry cooperation for the semiconductors. Also, another application for the wideband semiconductor is the LED or the optoelectronics. Maybe in China, it has the largest market. Solid-state lighting is reached 78 billion yuan, and maybe a little increase of the year-on-year. General lighting remains the largest market, over market share of 45%. Now the mini and the macro LED is also, as a new display technology, is a hotspot in China now, has maintained a great trend, especially for the display. And the demand for AI drives the rapid growth of high-end optical modules and optoelectronics efficient technology with broad industrial prospect, especially for the power electronics. We think the AI will drive the market is also for the power electronics in China. Okay, next class. Okay, for another application is RF. We think the RF market reached 10.29 billion yuan last year, and year-on-year increase of 16%, mainly driven by 5th generation communication infrastructure and the domestic gallium nitride RF electronics market has maintained the rapid growth. Another hotspot in China is the ultra wide-bandgap semiconductors, is especially for the R&D, such as the gallium oxide, aluminide, and the diamond. Now in China, for the gallium oxide, minimum laboratory size of 6 inch. And there are still many technical bottleneck, we think. First, the large-scale substrate and the epitaxy, and N-type and P-type doping and activation. Also, the material processing, especially for the diamond, is very hard. In China, for the equipment, manufacturing capability is improved. For the silicon carbide substrate and the epitaxy, also for the chip process, the Chinese equipment manufacturing is improved. But still, some key equipment still relies on imports. For the packaging testing equipment and some testing equipment, there's still a gap compared to the international standards, mainly for reliance on import in China. Now in China, the regional industrial cluster are rapidly formed. Maybe 4 major regions. First is the center of Beijing. We will call the Jing-Jin-Ji, is Beijing, Tianjin, and Hebei province. It has the strongest R&D in this area, and whole silicon carbide industry chain, and R&D is the most the R&D is in China, and this area is the strongest. And the second region is for we call the Yangtze River Delta, maybe include the Shanghai, Jiangsu province, Zhejiang province, and Anhui province in this area. This area have the high industrial concentration these years, and have the gallium nitride whole chain, and large new investment, and producing capability in silicon carbide. The third arrow is called the Pure River Belt. It's mainly Fujian, and as a center for Xiamen. It's the important concentration of LED industry in China. Now, it also began to extend towards to RF and the power electronics. And the last is the Pure River Delta region is the most largest application in China, and it may build for the cheap manufacturing capability now. And other reasons, for example, is the Wuhan, with a solid foundation in the optoelectronics industry, and now is focused on development of compound semiconductor. And another city is Chongqing. Yes, Sun, maybe a Chinese company, and ST jointly build a full chain silicon carbide production line in Chongqing. And this year, maybe next year, it will mass production now. Now we have opportunities and also challenges in China. We think the wide-bandgap semiconductor plays a crucial role in the global transformation towards to intelligent and sustainable electrification. But in China, the company, we think, is still small, scattered, weak, and low-level competition. We need to strengthen industry chain collaboration. Also, standards and testing, quality system, and the talent in China need to be strengthened also. And the third part, we will give a brief introduction of CASA. CASA is for China Advanced Semiconductor Industrial Innovation Alliance. We are NGO, maybe more than 300 members in our alliance, including the main university, institution, company in China. Our mission is to promote the development of collaboration and to promote the innovation system and the industrial ecosystem. Here is our member for our lines. Is CASA established a standardization committee and initiate the development and group we call the group standards. At present, there are 118 participation members and 140 observer members in our committee. And also to have 2 working groups have been set up for the silicon carbide and the gallium nitride power electronics. Yes, as a line, we build an information exchange platform for the industrial universities and the research institutions. CASA will release, every year, we will release a report called the Wide-Bandgap Semiconductor Industrial Development Report every year. This report will track the latest developments and release the industrial data. We are the only organization to release the industrial data in China for the wide-bandgap semiconductor. And through the organization, the International Wide-Bandgap Semiconductor Forum meeting, we will to promote a platform for the in-depth exchange technology and the typically industrial applications. We also help the government to make the plan for wide-bandgap semiconductors also for the government and the local government. Yes, we promote the application, especially for the vehicle in China, for the driving. We call the driving technology innovation, to promote the application of wide-bandgap semiconductors in field of new energy vehicles. We organize the research project and demonstrate for the application and the technical standards for the power electronics and used in the new energy vehicles. And we also help for the tech transfer, especially for the international innovating and enterprises. It's especially for the stand-up company into the China. We will provide the service for the collaboration funds and the applications. We will stand up a service system for the company to China. You're welcome to China for the through the system to China. Here is the summary. We think the wide-bandgap semiconductor industrial, especially power electronics chain, will be continually improved, and the market will continue to grow rapidly in China. And it's a common sense that wide-bandgap semiconductors are starting laying a significant role in sustainability, green energy, and emission reduction. International collaboration is very important. It's a trade despite some negative geopolicy influence. And CASA will continue support the collaboration of global wide-bandgap semiconductor industrial and academic. As a bridge and facilitator, we will promote to build international open innovate platform to create mutual benefits based on win-win principle. We think global changes, global opportunities, and global cooperation. At the end of my report, there is a little advancement. Yes, we will hold a company. It's the 10th International Forum on Wide-Bandgap Semiconductor in China, will be held in Suzhou in November. It's the largest forum for the wide-band semiconductor in China. Welcome to China to attend this meeting. The November is also a good time for the Chinese craft. Welcome to China. Thank you.
Thank you, Lubing Zhang. And now it's coffee break.
Thank you very much, Mitek. So first of all, thanks, Mitek, for inviting me to share my personal view, and especially Mitek bring this excellent weather to here. Thank you very much. Next, I can do it by myself. So my title is not directly wide-bandgap. It's about a back-end industry in Europe. And it's my short bio. I worked many years for Philips Semiconductor and NXP. And now 10 years ago, I quit my Philips job as a full-time professor. I would like to mention this IWBGPEAW ITW because Victor gave an open talk, but he didn't mention he's the chairman for IWBG ITW technology roadmap. And that we initiated with a Japanese colleague, American colleague, European colleague in 2017. And Victor is the chairman now. I think this roadmap is going to play more and more important role for wide-bandgap development globally. And I would like to quickly touch 3 subjects. One, the trend of packaging or backend. So packaging, I'm not talking about just the molding compound one chip. I talk about the packaging and also module and system development here. So this is a PowerPoint I made in 2003, was used by ITIS, International Technology Roadmap. I think most of you know this PowerPoint. I think this PowerPoint still covers the technology or product trend of semiconductor. So I'm not talking about the EDA, I'm not talking about the equipment, I'm not talking material. If we talk about semiconductor process technology development, this one PowerPoint can give you a good overview. First, let's look at the horizontal line we call Moore's law or more than more. Yeah. So what happened? We all know chip get smaller, 3 nano, 2 nano. The TSMC already can achieve 300 million transistors, 1 square millimeter. So a lot of colleagues say there's the end of Moore's law. Is that true or not true? I can show you one PowerPoint. This is my colleague. ISiCPEAW CTO, Mark Brick, he retired a few months ago. And according to this ISiCPEAW roadmap, we can go at least a decade to go from a nano to deep nano dimensions, ASTRON. So Moore's law will not finish in a short term of times. So we'll go certain period of time. So this is one thing. But if you look at the vertical line, there will be a physical limiter for Moore's law. Yeah, there will be a physical limit for CMOS, whatever we do. But now, even 20 years ago, Europe, ENIAC program, we're talking about beyond the CMOS. That time, there are many alternatives. Now we think maybe quantum computing can be the most promising beyond the CMOS technologies. So I'll talk about the vertical line, about computing, about the memory, or about the Moore's law, or even beyond CMOS. And the horizontal line, we're talking about more than more. It's about the function enrichment, because 20 years ago, we already discussed, as a healthy person, you only have a smart brain is not enough. What we need to have all these other capabilities, power, lung or organs, the power as a function of a healthy person. So that we call more and more, compared with all the other functionalities. So this wide-bandgap is one of the most important technology-driven more and more development. Power electronics, RF, optoelectronics, and photonics, and so on. So wide-bandgap is play a crucial role in all this more and more technology. So, and then let's talk about the packaging. We have these memory chips, computer chips, AI chips, whatever. We have the more and more, all the other functionalities. And the diagonal line is about integration, is about the packaging. Because all these nano, micro functional device, they cannot function alone. If you give you a nano chip, make no sense. So you need to wear this packaging heterogeneous system integration and to link these micro nano devices with applications. And here we have a 3 level of packaging, or we call it heterogeneous integration. We can do wafer level, chip to wafer, wafer to wafer, and chiplet. We can do in the packaging level, system and package. We can also do the substrate levels. So today is a very good example here, show this embedding this silicon carbide chip inside pre-circuit board. But we have also other challenges for assembly technology. For example, micro LED. If we want to assemble a display, we need to assemble tens of millions micro LED chip smaller than 10 micron, a big screen. How to do this? Pick-place semiconductor technology can never work. So we need to develop a self-assembly, mass transfer. And on the other hand, this micro LED technology can also help chiplet technology development. So in all these 3 levels, wafer level, component level, assembly level, there will be a lot of challenge for heterogeneous integration for packaging. And then here I pick up some typical feature set for backend technology for packaging. The wide diameter, we do wide bonding, smaller than 10 micron. The interconnected pitch nano level wafer scale packaging, smaller than 5 micron. Thickness cope trace inside print circuit board, thinner than 5 micron. Micro via diameter, small 5 micron. And wafer thickness, 8, 12-inch wafer, we can grind thinner than 20 micron. And also chip size smaller than 10 micron. What do I want to see? What I want to see, not only the front-end wafer technology, the back-end packaging, assembly are also go beyond our visualization. So when the semiconductor industry, when we talk about semiconductor Moore's law, people always say, well, front-end is high-tech, back-end easy. It is not true today. Certainly not true for the future. And these are the challenge for back-end technology. It's not only one chip functionality, it's a multi-functionality. We have to deal with multi-loadings, thermal loading, mechanical loading, vibration loading, chemical loading, and multidisciplinary, multi-technology, variabilities, material, interface, process, skill, failure mode, and damage, and the testing target. These are technology. On the other hand, it's modern technology. We have to deal with, because these backend are have diverse applications. So we have to deal with different type of small or mid-sized application need. Innovation complexity, we need a lot of talent, packaging engineers, and supply chain business model infrastructure, and also strong competition here. Europe now is not leading in back-end industry. I will come a little bit more back. And very important, talk on back-end, very, very important for the future. Back-end will offer more values, not only protect and thermal management, it will create more value for system. So, okay, I only showed one, sorry, not so fast, version. I showed one example. As my team in university, we try to make a roadmap for this power electronics module. And then we will dream in the long term, 5-10 years, we can have all corpus interconnect, and we can also have intelligent wide-bandgap semiconductor SOC, combine the CMOS with the sensors and also with MOSFET, whatever power devices. But this is long-term dreams. But simple CMOS wide-bandgap can already be done. For example, Fraunhofer ISiCPEAW, we have many years of collaboration, but they cannot compete with this silicon CMOS technology. But at least we need the dream, right? And talking about the heterogeneous integration packaging is not only semiconductor packaging. If we look, I made a comparison, similarity comparison. We have electron, we do electronic integration. We have a photon, we do photonic integration. We have a quantum, but quantum is not similar. It's not similar, let's see, a physical parameter. But conceptually, we can compare these three different technology. So if you see the electronic component, we have transistor, diode, photonic light source, resonator, modulator, and quantum component, we have a qubit, a quantum gate, and so on. So they are very strong interlinked together. So that's why 2 years ago, I initiated a seminar in Netherlands. So we'll see what are the competitive strengths in Europe. It's not only semiconductor electronic heterogeneous integration, but also integration photonic, quantum, and electronics. But certainly in short term, photonic or quantum will not generate economic value, but mid or long term, I think they might become one of the competitive advantage for Europe. Okay, so this is a couple years ago, time goes fast, I made a statement. I see about 441 million years ago, there was no animal and no plant on the earth, but only single cells. And starting from Cambrian time, something magic happened. This single cell was interconnected, integrated into together, and then we can have a splendid water today. So if you look at semiconductor today, the whole value chain, the front end specialists, they can create many different type of complicated devices, nano micro devices. It is a big challenge for packaging and system integration professionals and to embrace this mission to integrate, connecting all these devices together to transform this individual device into high-value system. So I called that time, create electro-Cambrian explosion by packaging and heterogeneous integration. So that is my personal vision, see how important back-end industry today, but also for the future. Pact for EU. So you will be curious, what is Pact for EU? So this is, I will not talk about it. This is a consultant group to provide suggestion recommendation for European Commission, because when US and Europe started CHIP Act plan, all the focus are on the front end part, not the back end. So last year we said, hey guys, we forgot something. If we only have a front end technology, we have no back end, then the supply chain will be issue, and also, the whole system may not function. So we start a recommendation advisor group and trying to provide some suggestion recommendation for European Commission. And these are the core team members. We have more than 40 industry members associated. But before talking about our progress, I would like to show how US is doing. We all know the CHIP Act, and I think it's November, October last year, and US released this backend National Advanced Packaging Manufacture Program, and they covered chiplet system, co-design, advanced packaging pilot line, material, photonic, and power, very important, thermal management, power equipment tool, material substrate. Compared with the European way of working, what is unique here is not about the content, it's about this, $3 billion. Within half a year's time, $3 billion available to start this backend program in US. And what we have been doing in the Pact for EU, so we set up a consultant group, we have different work package, and personally I'm in charge of this workforce development, and we want to know the offer side, the capability in Europe. We also want to know the demanding side in Europe, and what are the national, regional initiative. So we have done quite a lot of work. We sent more than 1,000 investigation to the inquiry form to all the different stakeholders in Europe, and we get 109 feedback. They cover academic, industry, and universities, and different type of sectors, different countries. And what are the conclusions that we found? Number one, if you look European R&D funding so far for semiconductor, very small amount went to back-end technology. Excel program, horizontal program, mostly at the front end. So this is one conclusion. And this is my personal view. If you look at the industry studies, I think we have increasing strategic need for back-end technology for Europe. And then we have a strong equipment, professional electronic and IDM, and a strong research innovation capability, including sustainability, green. We are weak in advanced IC and packaging fabrication, material supply. We hardly had any OSA, very little. And weak consumer electronics, weak industrialization pilot line for backend. Workforce talent shortage, and very, very important in Europe. We all know decision-making efficiency, long-term vision, and commitment. Because in Europe, we have a lot of small countries, and now every few years you have a new government, then they change the policy. You know the Netherlands, I came from Netherlands, we have a new government, we had election, but until now still no government, right? What is more problem? Very important, and we need to do more design for X in Europe. If we want to realize the CHIP Act ambition, that means we do manufacture here, create a product physically in Europe, then we need to know how to handle design for X. Design for functionality, design for reliability, design for yield, design for manufacturability, design for cost, design for security, design for sustainability. If we don't have this skill, it never can work. We can never get industry back to Europe. And also very important, the pilot line discussions. I think some of you are aware, Europe CHIP Act already, the first batch announced the 4 big pilot line. It costs billions of euros, and the next call will come more smaller scale pilot line. But we don't have this really high TRL level pilot line for backend. Fraunhofer is going to do the heterogeneous integration, but we don't know whether they have the capability, skill to support all this need, all the other companies, especially SME academic. And also very important, we found out, because Europe is going to develop this design platform. A lot of money will go to the common design platform, but there was no packaging tool. So we already informed European Commission the packaging design tool should be there, must be there. Okay, talent. Do we have enough people in Europe? So we have this inquiry form, and most colleague countries said we do need international talent to serve, because in Europe we don't have enough people here to work on this industry. And just the two examples, the Intel fab, backend fab in Poland, and also one Silicon Box, they intend to set up a big backend operation. They need already 6,000 people if everything goes well. And don't tell all the others, each country. Last week I was in Romania. They have also quite a big national initiative to the backend, so need a lot of people. So, conclusion. What is my personal view? Number one, this is a recommendation we are going to talk with European Commission. And number one, the CHIP-JU, it used to be the Excel program, now they changed the name, CHIP Act called CHIP-JU, need to substantially increase the budget, support the backend related research and innovation. Do you agree? Yes. So one of the purposes I come today is not to share my personal view. I want to get input from you guys. After this meeting, the conference, please drop me an email. I will try to put your input into final recommendation. Number two, CHIP-JU support prioritized backend technology development, and also design for X, co-design to enable EU competitive edge in packaging. What do we mean co-design? Material, process equipment. We need to do co-design. We are strong in equipment, not very strong in material. A lot of backend material, we are not very strong. But material, equipment, also system. Yeah? So co-design, front end, back end co-design. These are very, very important. And design for X. Industry policy, European Commission and public authority, each country need to develop, implement attractive industry policy and growth fund to support the startup, scale up back-end industry chain, the whole chains. So I don't know Sweden, the Dutch government said, we don't have industry strategy because that is not the government responsibility. But if you really want to get industry, semiconductor industry running to gain certain leadership, you have to have industry strategy. Yeah. Everyone doing this. So last year, December, I was with Dutch-Belgian delegation with the US, Phoenix. You know how US is doing. It's really, really unbelievable. So how the government are pushing the development of this industry. And then workforce development. And no people, no knowledge, we have nothing. So we need to support establishment, advanced education, training infrastructure for backend. I talked with many universities, and I can tell you guys, and we have very limited university have a specialized backend program curriculum, and even no clean room. If you want to do wafer level integration, wafer level packaging, you don't have clean room. Come on, right? How can you train people? And then, very important, we need to develop a pan-European collaboration program on multi-level talent workforce development, from technician levels and to research, engineer, designer. Facilitating SME, because backend, compared with the front end, we can really generate a lot of startup companies, SME companies, have their unique marketing segment expertise. But we need this the small to mid-scale industrialization pilot line to help them, because this big pilot line, like Fraunhofer and IMAX, may not have this, let's see, reach to help them. So we need this pilot line. And also, we are now talking with the Fraunhofer, this Fraunhofer system integration pilot line should provide certain attractive access to education and also to SME. And finally, international talent. And we need, and we are also calling for European Commission from European level to issue certain policy. Not 100% depends on each country government. Finally, this is my statement. European CHIP Act ambition cannot succeed without a joint EU vision strategy and, very important, implementation advanced packaging. Thank you very much.
So I will chair the next session on gallium nitride and silicon carbide devices. And the first talk will be given by a representative of Wolfspeed, this is Daniel Hoffman, and he will talk about how silicon carbide is going to conquer e-mobility. Your stage is yours, please.
Thank you very much for giving me the opportunity to talk today. SiC on its way to conquer e-mobility. We have many different applications, so I would like to address a bit of a new field for silicon carbide in this talk. However, I'm going to start with laser pointer doesn't really work. With a quick introduction to Wolfspeed, most of you already know, but some key figures. And then I'm going to introduce the dye technology and what we have a bit new here, and then focusing on the e-mobility on water, and then concluding my talk. Introduction to Wolfspeed. So we have a pretty decent number of years in experience making silicon carbide substrates. From the substrates, then we made devices, starting with Schottky barrier diodes, and then MOSFETs. The first in commercializing silicon carbide to the market in 2011 was the first SiC MOSFET. Proven efficiency, you already know, this is 10 versus 1 over silicon IGBTs. We have a proven field reliability of more than 12 trillion hours in the field of our devices. And we are kind of the pioneer in making the substrates. And we see two pictures here. On the top, this is our Mohawk Valley fab. This is a 200 millimeter, so the 8-inch fab. It's also heavily promoted. And below the picture, is this one better? This is the pointer. Okay, because the red is not working so well. Okay, maybe a bit. Let me get up here. This is a Silo 30, which is the new materials fab that we are currently building. This is entirely materials, making the substrates, crystal growth, to provide and supply the market with the material, which is on high demand. We have seen on most of the slides, we supply a majority to the market, also from the device perspective to our competitors. But this is really to secure the supply chain in silicon carbide, which is booming. But it still takes time to build up such facilities. Dye technology, a very famous picture here with all the contributing resistances. However, as you know, channel resistance and drift resistance are actually the key contributors to the RDS(on). As you can see, we have a very decent planar structure. We are still on planar structure. We are working on trench as well. However, the performance was never outperformed by the planar. And then when we also take some field advice, they more care about performance than the gate structure itself. Okay, then so overall target, decrease the cell pitch, getting smaller, get more cells, MOSFET cells per area, and then increase the power density, which is then challenging for the packaging, and tomorrow we're going to talk about it more. So the more power you have on a die, you have to get it out somehow. We accommodate a few layouts. You see here the gate pad. We have dedicated auxiliary Kelvin pads. This is mainly depending on the customer who's making a certain kind of package. So it's a bit customized here. And overall, as you know, we always target to optimize the switching behavior for several layouts. And one of a nice feature in our device is that we have a low temperature coefficient, so the RDS(on) over time doesn't increase that much. Talking about latest die technology, increasing switching speed, the generation which is coming out pretty soon has a highly focus on the body diode. Plenty of applications struggling with the snappy reverse recovery of the body diode, which we solved in the new generation. It's a quite soft body diode, which helps even switching faster. You can reduce turn-on losses of the complementary switch. So this is really a key feature, which is a bit unique in the market. Yeah, low conduction loss over temperature. I was addressing this already, quite stable. And then the resistance to the parasitic turn-on. As you switch faster, you always have to deal with transients. You have to deal with fast slopes, and you have to deal with plenty of packages. Some are more resistant to parasitic turn-on, some are not. So it comes down to the packaging if you would like to take out the full potential of silicon carbide. However, in the parasitic turn-on, there is more than just the VTH, but getting there soon. Yeah, this is the temperature, the RDS(on) over temperature that you can see here at room temperature. This is the rated RDS(on). And we have about 1.7 roughly when it comes to 175 degrees C. Yeah? This is quite helpful if you design your system. You always have the marketing value of the RDS(on) at room temperature, which is not really helping in the application because your system doesn't operate at room temperature. What really matters is at the range of 125, and then for overload conditions also up to 175 or even higher. So the devices are really nice for high power applications and conditions, since the RDS(on) is really quite stable over the temperature. Parasitic turn-on, and let me start here with VTH is only half the story. So we have the threshold voltage, it has a negative temperature coefficient, which means the higher the temperature, the lower the VTH. However, this is only half the story because the capacitance ratio matters. Because once you need to charge the capacitances to make the device switch on, right? And if you have a certain value for the capacitance ratio, you really make the device resistant to a parasitic turn-on because it still needs time to charge the capacitances until the device turns on. Which means even though you are already maybe above the VTH, it doesn't necessarily mean that the device is turned on. And here, this is a common, well-known event. So the top device here turns on. Then you get a positive DVDT on the bottom device, which is introducing or inducing a current into the gate, the CGS, which is then raising the VTH. And then once you are above a certain value, usually it's 2.5-ish, the device starts to conduct. However, as said, if the capacitance ratio is high enough, you still need time to charge those capacitances, which means the device is still in blocking mode and not switched on. Yeah. E-mobility on water. Mentioned new applications. Silicon carbide is not only used in EVs, but also in others. And we see that the water applications is quite interesting also for silicon carbide. Yeah? So this is a CAGR of 12.7%, which is based on the total available market for the water electrification, which you can see here on the right-hand side. So it goes from submarines to e-boats, tankers, so big ones, and then here the recreational ones. I'm going to address a quick study based on the passenger ferries that you can see up here, because all the mobility on water, they are exhausting in a lot of carbon dioxide. Yeah, you may know all the guys who have a nice vacation on the AIDA. It's also a high contributor to pollution to the environment. And if we can get the electrification on water, we can reduce the global footprint of carbon dioxide. Here on the left-hand side, so this is based on modern intelligence, the CAGR. However, It's quite an interesting number of the growth rate for water applications where we can put in the electrification, which means we can also put in silicon carbide. Kind of a busy slide here, but those are all the power conversion systems inside a boat. We have the main inverter for the propulsion, you have fuel cells to generate power, you have pump and fans actuators, so everything which is related to auxiliary drives, opening doors, lifting stuff. And so we have different power classes to request. Usually for propulsion, it's more like in the high power up to 1 gigawatt range, depending on the boat, and then goes down with all the auxiliary power supplies. We have a few, not technical challenges, but application-specific requirements, which is lifetime and usage. So those boats, they run for many years, 20 plus. Weight matters, which means the power density is really a key point here. The lighter, the better. And we have a bit harsh environment. So it's a lot of vibration, it's humid, it's salty, which then comes back to packaging. If you have a good package, which is also a bit resistant to humidity and harsh environments, it helps a lot. Also the dye, We cover plenty of power classes. So I was addressing the bare dyes in the beginning, but starting from discrete solutions, the standard TO247, 3-leg, 4-leg, the 2SEC3 with the 7 pins, leadless, then the quite common, well-known, also easy packs. You may know this from Infineon, but we scale from very low 200 watt up to couple of hundred kilowatts, and if you put them in parallel, even up to megawatts. So we got a quite wide range of devices and packaged devices that we can use for application-specific solutions. Now moving to a case study, especially on the passenger ferries. And here you can see that in Germany, if we count the passenger ferries, we have a total carbon dioxide emission of about 309 kilotons. What can we do here? So if we have how to bring the emission down, this is the electrification. And here for this case study, which you can see here on the right, this is the case one. We are focusing now on the electric ferry, which is less than 150 meters long and which usually operate less than an hour. This is for commutation. Especially in the north, you have connections between Germany, Denmark, Germany, Sweden, where you carry also trucks and passengers. And this study was actually done by Siemens, decarbonizing marine transport. So we are referencing to the Siemens study here. And if we now focus on this case one, where we have the full electric ferry, and let me move to the next slide here, you can really see that we have a potential carbon dioxide saving of about 134 kilotons, which is 43% reduction from the initial 309 tons. This is only the electrification. If we now consider moving from IGBTs, from silicon technology to silicon carbide, which usually brings up the efficiency by a few percent and over time can save tons of energy and can reduce the CO2 footprint globally. So here you can see even further reduction of the CO2 by using silicon carbide. Ferries operate up to 30 years, which means we need robustness and reliable products. It's not only the dye, it's also the packaging again, which needs to withstand and operate for such conditions. You are probably familiar with railway applications. They also have their own specs and requirements for the operation. Railways also they drive in high altitudes. They vibrate a lot. They drive next to a river, so it's also very humid, very hot, very dry, and very cold. So this kind of what we can also adapt here for the e-mobility on water. A few words on solutions. So this is a reference design here using the XM half-bridge power module, which is quite compact, low inductive, robust, and reliable. 3 of those guys are in a very compact 300 kilowatt reference design inverter, which is quite popular. It was a very high power density. It's water cooled, quite well connected to the sink, and low inductive. On the right-hand side, you see the difference if you switch at 10 kilohertz up to 20 kilohertz. Of course, the switching losses start to dominate, which means you have a lower efficiency, dependency of the output power. But if you switch at 10 kilohertz, you can really go up to 300 kilowatt at more than 90%, 99%. In terms of the auxiliary drives that we also need to address for the ferry applications, we get the base plate-less power module here, which is called the Wolf Pack. It is a 6-pack power module, base plate-less, quite easy layout. The pinout is also adapted to others in the market, let's say. A 25 kilowatt reference design, 3-phase inverter for auxiliary drive, for instance. And here we did a comparison between silicon carbide and IGBTs, and but this is pretty obvious. If you increase the power at the losses are getting higher and higher for IGBTs, while for silicon carbide it's pretty flat all across the power that we get out, which means that we can really make a difference by moving from silicon IGBTs to silicon carbide. Concluding my talk, using latest die technologies, which is we try to lower the losses, we try to switch as fast as possible. It's high DVDTs, high DIDTs. We would like to increase the efficiency, and then it helps that you have a quite stable RDS on over temperature. It's not increasing too much, and especially the soft body diode for the new generations, it's going to help a lot in faster switching, especially in DC-DC applications. We have a huge opportunity to further contribute to reducing the carbon dioxide emissions, especially on water, and in that case, the electrical ferries. For that, it's mandatory that we have a robust and reliable products which can withstand the harsh environments. Thank you very much for your attention.
So I think we have time for a couple of questions, if they are in the audience.
There you go.
Yes, please.
Can you show me improved reverse recovery? I'm not allowed to, so it got rejected by by some people. So we have very nice reverse recovery waveforms. As said, I'm not allowed to show it. Also at high temperature, especially at high temperature.
Is it on generation 3?
No, it's a different one.
Next one.
Yeah.
Any more questions? Yes, please.
Daniel, just a short question. Dieter from ISiCPEAW. Your next generation, is this the Gen 4, which you just recently released, or is this another one which is just coming out after this one?
This is the Gen 4. Yeah.
So this means there will be public data available soon?
Correct. Yeah, it's not that far out. Yeah.
Okay, thank you.
Yeah, one more question.
Yeah. This is a 1200 volt device. Yeah.
Yeah, thank you. I think
this is a whole device. That was the question.
Yeah, correct, for the aerosol.
Yeah, let's thank the speaker again.
Thank you.
And we're coming to the next presentation, which will be given by Martin Domé from onsemi. And she's, working here in Sweden.
Oh, thank you for your nice introduction, and thanks for the invitation. So my name is Martin Domé. I will give a talk today. I changed the title a little bit. It's called Reliability, Body Diode Operation and Parasitic Turn-on, 1 semi-1200 volt planar SiC MOSFET. And yeah, important co-workers who did experimental work here, Agnimitra, Sarah Kokoska, Sotirius Maslukas, and Tan Pam, who did the real experimental work here. How do I move this one? Sorry. Let's see. This way. Ah, this way. Ah, okay. Oh, thanks. It's okay? Okay, thank you, sorry. Okay, so the outline is the following. I'll talk about onsemi and silicon carbide MOSFETs briefly. Then on reliability topics of AC gate bias stress to look at the positive VTH drift, body diode forward bias stress regarding bipolar degradation, and also a little bit application aspects, channel conduction in body diode, and the parasitic turn-on of the high side device. So little brief on onsemi. onsemi is 33,000 employees with headquarters in Arizona, 8.3 billion total revenue US dollars last year, and larger than $800 million last year. So yeah, I'm claiming to have 25% market share and growing 2 times the market. We'll hear more about market shares tomorrow in the joint development report. And onsemi is today, since some years, vertically integrated after the acquisition of GTAT. We have our own crystal growth in the US, wafering in the Czech Republic, including epitaxy, and also wafer fab in Bucheon, Korea. And then we have assembly in different countries, different discrete packages and modules. So I will not present anything on specific products today. And this is just a little highlight press release from last year's October. So there is a big investment ongoing in the Bucheon wafer fab in Korea. Currently, the 150 millimeter wafer fab, previous silicon fab, is turning into, or has turned into, a pure silicon carbide fab with lots of tools, new tools going in. And there is also preparation for 200 millimeter wafer fab production in Bucheon, Korea. And plans to hire almost 1,000 employees over the next few years to ramp up production. To the technical side. So I will talk a little bit about threshold voltage drift during AC gate bias stress of silicon carbide MOSFET. So when applying a positive gate bias to the gate, then electrons are injected into interface states at the oxide. Negative charge shifting threshold voltage going positive. And when negative voltage is applied, electrons are released, holes may be captured, and threshold voltage moves negative. So this is known since long time. It is a fully recoverable effect. And a few years ago, Infineon presented also a permanent drift due to AC gate bias stress, shifting between negative and positive VDS. And that seems to cause some interface state generation and a permanent shift of VTH. And this is what Agnimitra here in the audience has investigated in his master thesis together with KTH. This is showing a little bit the measurement. So we measure threshold voltage always by applying first negative VDS, positive VDS, then measuring the threshold voltage after that to have a reset and to be able to measure permanent shift. And here Agnimitra looked into the dependence of different VDS on voltages. So lower graph here to the left. Let's see if you can see. Anyway, with the minus 12 volt VDS off negative, that gives quite much positive VTH shift. Then you can see that increasing the VDS on, the shift is increasing. And after 18 volt, it's pretty stable. And you can see on the middle left graph that the VDS off is the critical factor driving the VTH shift. So if you go down to about minus 4 volt, not much is happening. But when you go further negative on this on semi-planar MOSFET, you start to see more permanent shift. So for that reason, you can see datasheets for SiC MOSFETs also often have typical or proposed operation voltage minus 3 volt. And going even higher, then there can be a reduction in the shift again. But that's a peculiar effect. important is to know that if you go too large negative VDS off, there is a risk for threshold voltage drift. And then Agnimitra also looked into when you're switching, you always have some parasitic inductance, so you can get some VDS overshoot and undershoot, and how does that influence? So he measured with both overshoots and undershoots to the left, and in the center with only overshoots, selecting the inductance, and to the right is only undershoots. And the conclusion is that the overshoot, if you have an overshoot and undershoot, you get more drift in threshold voltage. But when separating, it is actually the negative VDS undershoot that is accelerating the VTH drift. So yeah, there's likely some filling of traps, of hole traps fast that is happening. And that's important to watch out for the negative VDS and the overshoot. And then, measuring many cycles here, you can see then that the 2E11 cycles, which is often quoted to be around typical automotive mission profile for automotive drivetrain, we have about less than 0.3 volt shift, so it's not so bad. And the RDS-on drift, you can see to the right, is really small, thanks to the low channel resistance. And the right graph was measured with -8 volt VDS off. So that's even more accelerated. And then here in the left graph, you can see a comparison to a few devices on the market, competitor devices, using VDS of -8 volt, which is a very harsh condition. So that's outside the recommended operation area for all devices. You can see the on-semi devices, among the most stable devices. And to the right, we stressed very many cycles here up to the PV inverter mission profile, which is 3E13. So past 1E13 cycles, we still have acceptable threshold voltage drift with VDS of -5 volt and negligible drift with VDS of -3 volt. That's good to see. Now to the next topic. This is bipolar degradation in silicon carbide MOSFETs. So back in the days, this was a hot topic for high voltage diodes. Then it was a little bit forgotten when the silicon carbide MOSFETs do consist of a bipolar PN diode. So we have done, Sarah Kokoska presented high current pulsed body diode stress and going to very high current densities to provoke bipolar degradation and see where the limit is. So this is tested well outside the normal operation conditions of the silicon carbide MOSFET. So we do a careful pre-characterization, stress the body diode, and then do a post-characterization. And the parameter we have seen that is drifting, that is most sensitive to drift after body diode stress, that is RDS-on. So you can see when we improve the epi a little bit, what's called type B here, then we could suppress the RDS-on drift and go up to, this is after 1 million pulses, so we get then a really small RDS-on drift, even with 3,570 amp per centimeter square currents density stress with 1 million pulses. But when going to 5,000 amps per centimeter square, then we eventually see a strong increase of RDS-on. And we examined nothing strange had happened with the package, a wire bond or delamination, and then did some backsided electroluminescence here. So you can see to the right that we see the stacking faults there after very high current body diode stress as proof of bipolar degradation. And in the center, you see the unstressed device, which has very homogeneous electroluminescence. Now to the body diode behavior and parasitic turn-on of high-side switch. So for the body diode, in the left graph, you can see IV characteristics with VDS equals 0 volt. And in that graph, you can see that there is a quite low built-in potential of the body diode of about 1.5 volt where it starts conducting. And you know silicon carbide has a built-in potential of 2.8 volt or something. So this is conduction through the channel, which has a lower built-in potential than the PN junction. In the center, we have applied -5 volt to the gate, and then we have the regular 2.8 volt or so built-in potential. So, and it's interesting that the operation with VDS 0 volt has some benefits. As you can see, due to the channel conduction, we can have a lower forward voltage drop. And another benefit is that due to the channel conduction, we bypass the PN junction, and therefore we get less carrier plasma in the on state. So we can also improve the reverse recovery characteristics. So to the right, you see experimental circuit for double pulse measurements where we have the low side switch, and we look at the high side body diode here. And in this measurement, we actually see the measured current for the low side device, but the peak you can see during turn on is due to the body diode capacitive current or carrier plasma, so the recovery. And to the left, you can see that even for a pretty high DIDT with VDS 0 volt, there is no temperature dependence for the peak current. So it's basically a unipolar operation. So a good recovery, although there are oscillations due to parasitics of the double pulse setup. And in the graph to the right, you see we have applied VDS minus 5 volt. Then you see that when we go up in temperature, we get the larger peak. That's due to the carrier plasma and reverse recovery. So VDS 0, and that can lead to some snappiness also, as you see. So operating with VDS 0 volt is beneficial in terms of reducing the reverse recovery and improving the softness. And then, of course, VDS 0 volt sounds risky in terms of parasitic turn-on of the device, as Daniel Hoffman described very nicely in the talk before, the mechanism behind it for the high-side device. We did some experiments, varying designs here. So you can see the blue curves, design number 1, you see the input capacitance and the CRSS capacitance, which is basically the gate drain capacitance. We suppressed the gate drain capacitance significantly. And then in the center, you see the switching curve with the device with the low CRSS. And here we have done a thing that Antoine in the audience here introduced. He varies the external gate resistor of the high side device. It's 0 volt VDS, and then going all the way from 0 ohm up to 56 ohm. Higher external gate resistance will give sensitivity to parasitic turn on. And even with 56 ohm, design 1 has no parasitic turn on. But the device to the right, which has the higher CRSS, when you go above 20 ohm, you start to see significant parasitic turn on, which is not destructive, but which increases switching losses. So the design 1 has a high immunity to parasitic turn on thanks to the high CISS to CRSS ratio. And then, comparison to a few competitor devices on the market here, we can see that on semi-planar device with the improved CRSS, in the upper right corner, you see the CISS to CRSS ratio. You can see that we're clearly higher than the competitors, and there is no parasitic turn on, even with the highest external gate resistance. Other devices are still pretty good, I would say. But what we want to highlight here with this one is that the ratio of CISS to CRSS is the key thing for high immunity to parasitic turn on. And it's more important than the threshold voltage level, as you can see that one of the devices has a higher threshold of 4 volt, which many customers like to avoid parasitic turn on, but it's not the key thing. It's the ratio of the CISS to CRSS. So high VTH can be operated with. So the summary on SEMI is vertically integrated in silicon carbide, more than $800 million sales 2023, and production capacity ramping up. On the threshold voltage stability during bipolar AC gate bias stress, VDS off level is a critical factor, including the undershoot. And acceptable threshold voltage drift is shown for more than 1/30 cycles with VDS of -5 volt. On the bipolar degradation, we have a few percent RDS on shift for body diode stress up to 3,500 amps per centimeter square. But we can see some clear bipolar degradation after 5,000 amps per centimeter square, verified by electroluminescence. and then significant channel conduction with VDS 0 volt. And the software recovery can be obtained using a unipolar gate driver with 0 volt VDS. And high immunity to parasitic turn-on was verified with a CISS to CRSS ratio. And thank you for your attention.
So thank you very much for the presentation. So we have a couple of questions, I guess, from the audience. Yes, please. My microphone. Wait a second, yes.
Very, very quick one. The 800, you hear me? $800 million. Do you know by any chance what percentage of the revenue was that for that year?
In all of onsemi,
Yes.
it's close to 10%, or it's around 10%, I would say.
Right. Thank you.
More questions? Yes,
One
please.
right here. Thank you for an excellent presentation. My question is on the bipolar degradation. Your results are on 1200 volt devices, is that correct?
That's correct, yeah.
Do you have any idea of what the impact of bipolar degradation would be when you get to 3.3, 6.5?
Yeah.
With a higher drift layer? Do you have any information on that?
Yeah, I think like has been reported by some of the Japanese companies and groups. You get more bipolar degradation even without going to really super high current densities. That's what we would expect, but we have not tested that experimentally.
Thank you.
One more question from here.
I think one question regarding comparison that we have done for the devices and the shift of the regarding comparison that you have done, have you considered the same gap between the operating condition that they have considered for the gate voltage to the stresses that you have put on the device? For example, your device maybe work a bit, you recommended your datasheet -6 to +15, but then another manufacturer consider -5 to +, for example, 15. And then you, for all of them, you consider -8 as a stress.
Yes. So, and we did not consider that. So I mentioned it's a very harsh stress condition. So you can argue it's not fair to stress devices outside the max rating, but it's just to give a feeling what, how they compare the capability of VDS off.
Thank you. I think we will close the session before lunch now, and we will return back after lunch.